Hi there. Today I'll be showing you my Physics 1 final video from Mr. deLone's 2020 AP class. I'll be going over some physical demonstrations and explaining them using physics concepts. So I'd like to start off with saying that all of my physical demonstrations assume that there's no air resistance in each given demonstration. With that said, the force of gravity can be seen in each and every scenario with each and every object. But the past two scenarios with jumping off the rope swing and jumping into the pool specialize with the force of gravity. So the force of gravity can best be explained by mass times gravity, and that's how it's calculated. This is the downward force that pulls every object towards the surface of Earth at exactly 9.8 meters per second downwards, so negative. So this diagram best explains what was happening in the past two scenarios. So the force of gravity pulls me downward towards the Earth and accelerates me at negative 9.8 meters per second as I fall to the surface and through the surface underwater. This force of gravity, the only force acting on me as I fall, can be calculated using force of gravity equals mass times gravity. So we know that gravity is negative 9.8 meters per second. And in order to calculate the force of gravity, or the weight, you would need to know the mass of the object. So the past scenarios with the slinky going down the stairs can be best explained using simple harmonic motion. So the slinky undergoes a repetitive motion during constant time intervals. So the time for the slinky to go from here to here is the period, the time for one complete oscillation, and the frequency is the number of oscillations per second. The frequency and period can be related by frequency equals 1 over period. So simple harmonic motion can be shown through both pendulums and springs, but for the scenario of the slinky going down the stairs, it's shown through a spring being compressed and released. So two terms we should be using with simple harmonic motion are equilibrium and amplitude. Equilibrium is the middle point of oscillation where the spring or the pendulum has zero net force, and amplitude is the maximum displacement of the spring or pendulum from equilibrium. So in order to calculate the period of the spring, which is not affected by the amplitude, you'll need to utilize this equation, 2 pi square root m over k. So the m is the mass, in this case, of the slinky in kilograms, and the k is the spring constant in Newton meters. So in the last physical demonstration, you saw my family and I, with the help of my two dogs in the background, trying to balance and keep the seesaw at equilibrium. So this can best be explained by the center of mass. So the center of mass is the weighted average of mass in a system. So you saw my family and I, on each side, one person would stay constant and another would try and shift their weight and make the seesaw be at equilibrium. This can best be explained by Newton's first law. So we were trying to create unbalanced forces to accelerate the object and keep it at rest. And we were trying to make it at equilibrium, so the acceleration would be at 0, so it would be at rest. So these two equations, the top one for position and the second one for velocity, both for center of mass, can be utilized to find the position of the center of mass and the velocity of the center of mass using masses of both objects, the total mass, and the position and velocity to find the position and velocity of the center of mass, respectively. So in the past example, we saw the bike moving forward but also rotating. This means not only does the bike have kinetic energy, but it also has kinetic rotational energy as it's rotating. So in the beginning of the year, we talked about translational velocity, so an object moving forward with velocity in 2D motion. But later in the year, we introduced rotational velocity and rotational kinematics and energy. So this works with the example of the bike. So and in terms of energy. So the bike has kinetic energy as it's moving forward along the road, but it also has kinetic rotational energy as it's rotating forward along the road. So later in the example, I try and I squeeze the handbrakes and I try and slide it forward so that I will only have kinetic energy but not kinetic rotational energy as it's not rotating. But we saw that this didn't work, and this brings us to our next topic of friction. So these are the two form energy equations that we would be using if we were trying to use conservation of energy. So for the top one, this is the kinetic energy translational. So for this, you need the mass and the velocity in order to find the kinetic energy. For the bottom one, it's the kinetic rotational energy while the bike is rotating. So for this one, you need the moment of inertia and the rotational velocity. So for our last physical demonstrations, we're going to be talking about friction. So for each surface, I measured out a displacement of 1 meter using a ruler and drawing it with chalk. So you can see me dragging the ruler and the nail across both my driveway and the deck to show the two different surfaces and thus coefficients of friction. So friction is the force it's a resistant force that slows the velocity of an object. So you can see this with the ruler as I drag it through the air with the same force as I drag it along the ground, but due to friction it's slower on the ground and the time takes longer, and this can be seen with both the deck and the driveway, and so the coefficient of friction differs with these surfaces. So like I said earlier, friction is the force that opposes motion and the direction that the object wants to move in. And you saw this with the last example as the screw and the ruler dragged along both the driveway and the deck and slowed the motion and was resistant. So the force of friction can be found with the coefficient of friction, mu, times the normal force. So this is for kinetic friction because the object is sliding. So I wanted to add that the ruler was dragged along both the deck and the driveway to show the different coefficient of frictions along different surfaces. So the deck was wood, a little bit of a smoother surface than the rugged driveway, so the coefficient of friction would be slower. So over the displacement of 1 meter, the objects move faster even with friction. Thank you for watching my video on physics, and a big thank you to Mr. deLone for a great year of learning and EP exam preparation and some fun too.